In this presentation, I'm going to discuss the computation of elastic forces. Solid objects are referred to as elastic as they can deform under the impact of a force applied to the object. If the force is removed, then a deformed elastic object returns to its original shape. In the presentation, I'm going to introduce a general concept that can be used to derive forces for various types of deformations, and I will also discuss some additional aspects that are relevant for the simulation of elastic solids. In particular, I'm going to discuss contact handling with simple shapes such as planes and also rendering aspects. Here we have the outline of the presentation. I'm going to start with an introduction to elastic forces. Then we look into the concept that we are going to use to derive forces for various deformation types. After that, I will briefly talk about stability aspects, in particular damping and time step settings. Then, towards the end, we will see how to handle contacts with simple shapes, and then I outline a variant to visualize elastic objects. In graphics, it's quite popular to use different object representations for different purposes. For instance, a low-resolution representation for the simulation and a high-resolution representation for visualization purposes. And here I'm going to explain how this works. Now first we start with the introduction to elastic forces. Elastic forces are always specified for sets of particles. So 2, 3, 4 or more particles form an element. Then we estimate the deformation of such an element, and from the deformation we finally compute elastic forces that act at the particles with the aim to minimize the deformation. So forces at particles account for the resistance to deformation, where deformation can refer to various aspects. For instance, a line segment can be stretched, a surface can be sheared or bent, and volume elements can change their size. These different deformation aspects are illustrated in the images. We see a rope that is subdivided into line segments and particles. Each line segment consists of 2 particles, and if a line segment is stretched or compressed, we end up with elastic forces at the respective particles in order to minimize the deformation. In case of a surface, as shown in the second image, we typically work with triangles. So the surface is subdivided into triangles and particles. For the triangle elements, we compute the deformations, for instance stretch, shear or bending, and the respective forces are applied to the 3 particles that form a triangle. And the same idea is finally applied to volumetric objects. Here we typically use tetrahedral elements. So a volume is subdivided into tetrahedra and particles, and if a tetrahedron deforms, then elastic forces are applied to the particles of the tetrahedron. So in general, we have particles and elements. Elastic objects are subdivided into particles and elements, and we check whether an element is deformed or undeformed. If it is in its rest state, then we do not have elastic forces at the particles. However, if an element is deformed, then we get elastic forces at the particles that accelerate the particles towards positions that represent the rest state of the element. So forces are computed for elements and applied to particles with the goal to preserve the original undeformed shape of an element and for the entire object. As already briefly discussed, elastic forces are always computed for sets of particles that form elements. And we consider different deformation types that also depend on the number of incorporated particles. So if we have 2 particles that form an elastic element, which is a spring in this case, then we can just check the distance between the 2 particles. If this distance deviates from the rest length, then we have a deformation, which is either stretch or compression. And then in order to counteract this deformation, we apply elastic forces to the particles. If we have a larger number of particles that form an element, then we can consider more deformation types. If we take, for instance, 3 or 4 particles, then we are not restricted to the measurement of distances between the particles, but we can also measure shear and area or volume changes. The illustration shows a rest state with 4 particles, and if we have shear or some area change, then we apply elastic forces at the particles with the goal to restore the rest shape of the particles. That's it about the introduction to elastic forces. Now in the following I'd like to discuss a general concept that can be used to derive elastic forces from different types of deformation. So we start with some deformations that we would like to handle, and the concept allows us to compute forces that counteract this deformation. So the concept starts with the elements that are formed by particles. Very often we use so-called simplices as elements, which can be seen as the simplest shape in a certain dimension. So for 1D objects we would use line segments, for 2D objects we use triangles, and for 3D objects we use tetrahedral elements. Now for the elements we consider deformations or strains, and we define how to compute values that represent these deformations. For a spring, for instance, we can state that any change of its length should be considered to be a deformation, and then we would define that the difference of the actual spring length and the rest length of the spring is a measure for the deformation of a spring. In the next step, we compute the so-called stress of an element. This stress is typically governed by the amount of deformation and by the stiffness of an element. On one hand, elastic stress grows for increasing deformation. On the other hand, stress also depends on the element's stiffness. If we have two objects with the same deformation but different stiffness properties, then larger stiffness causes larger stress. The next quantity that we need in the computation of elastic forces is the elastic energy. This energy can be computed from strain and stress, and it represents the work that has been applied by forces to get to the current deformed state. So if we apply a force to some point of an elastic element, then the object deforms and the respective work is stored as elastic energy in the element. Finally, we compute the elastic forces at the particles from the elastic energy of the element. Here we basically compute forces that accelerate the particles into directions where the elastic energy is minimized. An undeformed element has zero elastic energy, so when we try to minimize the elastic energy, then we actually try to restore the original undeformed shape of an element. The computation of elastic forces with the outlined concept is actually motivated by specific properties that we get for the elastic forces. And here one of the most relevant properties is the fact that the elastic forces just counteract the deformation. They do not change the linear or angular momentum of a deformed element. If a deformed element travels at some speed, this movement is not affected by the elastic forces that are computed with the outline concept. So that's the overview of the concept, and now we look into the individual steps. First, we start with the definition of our elements. As already discussed, we very often use line segments, triangles, and tetrahedra. And the shape of the elements is described by particles. So line segments are represented by two particles, and the representative positions of the two particles describe the length of the element. If we have four particles that form a tetrahedron, then we can, for instance, compute the volume of the tetrahedron from the particle positions. In the illustration, we see the notation that I plan to use in this presentation. We have an element I, and this element is formed by four particles with positions xi1, xi2, xi3, and xi4. From the positions, we compute the deformation of the element, and from the elastic energy of the element, we get the forces at the particles. Now, based on the element, we define the deformations that we would like to handle. Here in this presentation, we use scalar values ci to quantify or to measure some sort of deformation of an element I. The respective function to compute the deformation depends on the particle positions xi1 to xin. So for a line segment, the deformation is computed from two particles. For a tetrahedron, we take four particle positions to compute the deformation or strain. In the general 3D case, the deformation or strain is represented by a 3x3 matrix, which allows to encode a larger number of different deformation types. Here in this presentation, however, I keep it as simple as possible, and we just look at deformations that can be represented with one scalar value. So ci is a scalar function that represents some deformation, and we state that the function should be 0 if an element is undeformed, and ci should not be equal to 0 if the element is deformed. The simplest example for deformation is certainly the stretch or compression of two particles at positions x1 and x2. If we consider an element I that is formed by these two particles with a rest distance Li, then the strain C of the element I formed by the particles xi1 and xi2 can be computed as the difference between the actual distance of the particles and the rest distance Li divided by the rest distance. The normalization is not necessarily required for the concept, but it is a typical convention that strain should be dimensionless. Here we see an illustration of an elastic object that consists of 5 particles, and the 5 particles form 4 elements. The green dots are the particles, and the dotted lines indicate the elements. Now we consider a strain function for each element. We have 4 elements, so we have 4 strain functions Ci that are computed as the difference between the actual distance of 2 particles and their desired distance in the rest state of the object divided by the rest distance. Now if the object is undeformed, all functions Ci are 0. If any of the functions Ci is not equal to 0, then the respective element and also the entire object are deformed. Here we see another example where our element is a tetrahedron and the points xi1, xi2, xi3 and xi4 form the tetrahedron. On the left-hand side we have the undeformed tetrahedron, and on the right-hand side we see a deformed state. Now how can we quantify the deformation of such an element with a scalar function? One simple option, for instance, would be the consideration of a volume difference. The tetrahedron on the left-hand side has some original volume or rest volume, and we could measure the difference of the original volume to the actual volume of the tetrahedron. This would give 0 for the tetrahedron on the left-hand side and a value not equal to 0 for the tetrahedron on the right-hand side. So the volume deviation is actually an appropriate deformation measure. Otherwise, however, it's actually not obvious how to define more complex deformations. And this is actually the major limitation of the simplified strain computations that we use here in this presentation. If we would use a 3x3 matrix to represent strain, then we could, for instance, represent volume changes in certain directions. We could measure that a tetrahedron is compressed in x direction but stretched in y direction. Or we could represent shear. Using just one number to represent a deformation does not allow to handle such aspects. Nevertheless, the concept for the force computation is always the same, independent from the complexity of the deformation function, and I would like to keep it here as simple as possible. The next quantity that we compute from strain is stress. So if an element is deformed, we have some strain and we also have some stress. And this stress depends on the strain, and it also depends on some stiffness of an element. Stress can actually be seen as internal pressure. If we have a deformed volume and we consider a very small plane inside the object, then one of the forces acting on this plane from both sides, divided by the size of the plane, is stress. How to get from strain to stress depends on the material that we would like to represent. Again, we keep it simple and just use a constant scalar value Ki as the proportionality factor between strain and stress. If you have soft material, Ki would be rather small. For stiff materials, Ki is larger. So for the same amount of strain, we generally get different amounts of stress dependent on the material stiffness. In the illustrations, we see an undeformed element with 2 particles, where strain Ci is equal to 0. In the compressed state, Ci is not equal to 0. And the strain in the deformed state also causes stress Si. The forces Fi1 and Fi2 show internal forces that act at the particles. These forces cancel the external forces that are applied to the particles to deform the element. If internal and external forces at the particles cancel, then the element remains in the deformed state. Now the magnitudes of the internal forces are related to stress. For a growing stiffness coefficient Ki, the stress Si is growing, and also the internal forces at the particles will be larger. Now when we apply a force at some point on the surface of an elastic element and the element deforms, then we do some work, and the work is stored as elastic energy in the element. The elastic energy of a deformed element is given as 0.5 times strain times stress times the volume V of the element. In our setting, S is equal to K times C, so the energy can also be expressed in terms of the strain as 0.5 times K times C squared times V. As strain and stress can be computed from the particle positions, the elastic energy is also a function that depends on the particle positions. It is obvious that the elastic energy quantifies the deformation of an element. If an element is undeformed, then the elastic energy E is 0. If an element is deformed, then we get some positive value for the energy. And now this energy is considered for the force computation. Our goal is to restore the rest shape of a deformed element with non-zero elastic energy. This goal can be achieved by minimizing the elastic energy. And this minimization can be achieved by accelerating the particles into the respective directions where the energy gets smaller. So in terms of the forces, we would like to accelerate the particles from positions with high elastic energy towards positions with low elastic energy. And the optimal way to do this is to accelerate the particles in the direction of the negative gradient of the elastic energy. When a particle moves in the direction of the spatial gradient, then we actually get the largest possible increase in the elastic energy. On the other hand, if particles would move in any direction orthogonal to the gradient, then the elastic energy does not change. As we are interested in minimizing the energy in an optimal way, we have to move the particles in the direction of the negative spatial gradient. And therefore we compute the respective forces. So again, our goal is to minimize the elastic energy, which corresponds to minimizing the deformation. Now, if we have an element I with particles xi1 to xin, then the force at particle j is computed as the negative partial derivative of the energy ei with respect to the position xij. The energy can be written as 0.5 times stiffness times strain squared times volume, which means that the partial derivative can be written as minus k times v times c times the partial derivative of c with respect to the position xij. This force accelerates particles into the direction of the negative gradient, which means we realize the largest possible decrease in the elastic energy, and the particles are accelerated towards rest state positions. The elastic forces Fij have to be applied to all particles j of an element. Otherwise, we do not get the special and highly desired properties that the elastic forces sum up to 0 and that they do not change the linear and angular momentum of an element. Now we look at an example. We consider two particles xi1 and xi2 that form an element I. We are in 3D space, so the particle positions have three components x, y, z. And in the undeformed state, the length of the element I is given by Li. Now we define some strain. We state that the scalar strain function CDI is computed as the difference between the actual length of element I and its desired length Li divided by Li. Here d stands for distance, which indicates that we consider a distance deviation in the strain function. Finally, the strain function can also be written in terms of the three components of xi1 and xi2. Now, for the force computation, we need to know the stiffness of the element, the volume of the element, the strain function, and also the partial derivatives of the strain function with respect to the positions of the element particles. And these partial derivatives are shown here for our example. In our case, strain is a scalar function, the position is a 3D vector, so the derivative of the strain with respect to the position gives a vector. As indicated here for particle xi1, we therefore compute the partial derivatives of the strain function c with respect to the x, y, z components of the particle. From the resulting term, we see that the gradient points into the direction of the line of an element, which is rather obvious. When the particles move along this direction, then we have the biggest effect on the deformation and the respective deformation energy. If the particles move orthogonal to this direction, then we have the smallest possible effect on the deformation state. Now, in addition to the gradient with respect to particle 1, we also need the gradient at particle 2 as shown here. Now we have all ingredients and we can compute the elastic force. The elastic force at particle xi1 is referred to as Fdi1, and once again d stands for distance. And the force is computed as minus k times L times c times the partial derivative of c with respect to position xi1. K denotes the stiffness of the element and L is its volume, which is a distance in 1D. Here we also see the elastic force that acts at the second particle xi2, and both forces are visualized in the illustration. As you can see, the forces act into the direction of the line between the particles, which corresponds to the gradient of the strain function, and which is the direction of the largest possible change that we can get for the strain. The other extreme case is a particle movement orthogonal to the line, where we would get a minimal change in the deformation, which is not our goal. As you can see, our derivation ended up with forces for elastic springs. So the result is not particularly exciting. Anyway, the goal was to illustrate the concept for deriving elastic forces, and elastic springs are the simplest example in this context. In the second example that I'd like to discuss, we move from a 1D element to a 2D element. So here our element is a triangle I formed by three particles xi1, xi2, xi3. As indicated in the illustration, our triangle has a rest volume AI in its undeformed state. And our goal is actually to compute elastic forces that preserve this area AI. Before we look at our strain function, I introduce some notation to simplify the expressions. So EI1 is a vector from xi1 to xi3, and EI2 is a vector from xi2 to xi3. So basically E1 and E2 are two of the edges of the triangle. Now we define the strain function CA. We would like to preserve the area of the triangle, so here we consider the difference between the actual area computed from the cross product of the two edges and the rest area AI. For conventional reasons, we divide the term by AI to end up with a dimensionless quantity. And the A in CA refers to the fact that we consider the deformation of an area. In order to compute the elastic forces Fa, we need a material stiffness Ka, the element volume, which is the area of the triangle, the strain function Ca, and its partial derivatives with respect to all components of all positions of the element particles. We follow the same steps that I've described for the spring, and then we get the forces that we see here on this slide. The term Si is a scalar value that is mainly computed from the stiffness and the strain function, and the force directions are given by cross products of two vectors. And these 3D directions are actually the most interesting aspect here. On one hand, all forces act in the plane of the triangle formed by these three particles, and on the other hand, each force is orthogonal to the edge opposite to the respective particle. So for instance, the force Fi1 is orthogonal to the edge Ei2, and also Fi2 is orthogonal to Ei1. Similar in sense to the spring, these forces are motivated by the goal to maximize the impact of a particle movement on the strain function. Accelerating a particle in the direction orthogonal to its opposite edge has the largest possible effect on the area of the element. Again, moving a particle orthogonal to the indicated force directions would result in the other extreme case, where the area does not change at all. And finally, it's also interesting to note that the forces are in the plane of the triangle. If we take, for instance, force Fi1, then we see that Ti is orthogonal to the plane, as it is computed as a cross product of two of the edges. And then we see that the force is orthogonal to Ti, as the force is computed from the cross product of Ti with some other vector. So Ti is orthogonal to the plane of the triangle, and the force is orthogonal to this vector, which means that the force is in the plane of the triangle. And this property holds for all three forces. The last example that I'd like to briefly discuss is the volume preservation of an elastic tetrahedron. Here we have a 3D element that is defined by 4 points xi1, xi2, xi3 and xi4. Again, we simplify the expressions by introducing variables e for 3 of the edges of the element. The strain Cv that we consider here captures the deviation of the actual volume from the rest volume Vi. As you can see, the actual volume can be computed from the particle positions. And the V in Cv indicates that we have a volume constraint. Finally, we see the elastic forces that we compute and apply at the 4 particles of a tetrahedron. As always, Kv is a constant that describes the stiffness of the element. Similar as in the previous examples, the force directions can be deduced by looking at the cross products in the expressions. It turns out that the force at a particle is orthogonal to the triangle opposite to that particle. It's obvious that we get the largest volume change for the tetrahedron if the particles move in these directions. That's it about some examples. We have seen how to derive elastic forces in cases where the strain can be expressed with one scalar value dependent on the positions of the particles that form an element. For the strain, one can actually use arbitrary formulations as long as the expressions base on particle positions. The same concept can actually be also applied to more complex deformations where the strain is expressed with a 3x3 matrix, but this is not part of this presentation. Despite the fact that I've just discussed a simplified version of the computation of elastic forces, we can nevertheless use the concept in a versatile way and for a large variety of materials and effects. Here in this video we see an example of an interactive simulation where we combine the forces for the 3 strain functions CD, Ca and Cv that I've discussed in the previous slides. The respective stiffness coefficients have to be defined, and then we can combine the forces in different ways. The cube consists of tetrahedra, the tetrahedra consists of triangles, and the triangles consist of edges. So for all edges, we consider the elastic forces that preserve the distance between 2 points, and for all tetrahedra, we consider the volume-preserving forces. In terms of the triangles, we only consider area-preserving forces at all surface triangles. And we set the desired rest area to 0. This actually means that the respective forces try to minimize the surface area of the entire cube, which can be interpreted as some sort of surface tension. Now the 3 force types can be combined in different ways. If we use distance and volume-preserving forces, then we have a deformable object. If we add the surface tension forces, then the shape of the cube changes towards a sphere. And if we just preserve the volumes of the tetrahedra but not distances between adjacent particles in the cube, then we get something that looks more like a fluid. So the proposed concept to compute elastic forces from strain is very powerful and versatile in terms of deriving particle forces for different types of material. And actually, the concept is generally used to derive particle forces. Later in the course, we will be talking about forces at fluid particles that can be derived with the same idea. The elastic forces that we compute from the gradient of the elastic energy have interesting properties, and these properties are actually the main motivation why we generally apply the concept instead of just using some arbitrary forces to counteract a deformation. One of the most relevant properties is the fact that the elastic forces just counteract the deformation. They do not change the linear or angular momentum of a deformed element. For instance, if we have a deformed spring that travels at some speed and also with some angular velocity, then the overall movement of the spring is not affected by the elastic forces. The forces result in accelerations that aim at changing the distance between the 2 particles of the spring, but the forces do not affect the linear and angular velocity of the entire spring. And this property holds for all elastic forces that are computed from the gradient of the elastic energy. Here on the right hand side we have a tetrahedron and we see some elastic volume preserving forces. Again, when we apply the forces to all involved particles of an element, then the forces only influence the deformation state, but not the velocity and the angular velocity of the entire element. The fact that elastic forces do not change the linear momentum of an element actually corresponds to the fact that all elastic forces of an element sum up to zero. And also, if you have an object with a certain number of elements, then the elastic forces at all particles of the entire object sum up to zero. In addition to this, the elastic forces also do not cause torque at an element. And that's why they do not change the angular momentum or the angular velocity of an element and also of an entire deformable object. In this illustration, I'd like to show the fact that a sum of zero for the elastic forces is not necessarily sufficient for not causing torque at an element. So if the sum of forces is zero, then the linear momentum is definitely preserved, but for the preservation of the angular momentum, additional constraints have to be fulfilled. I do not go into further details here, but the illustrated forces are not elastic forces. Elastic forces always preserve the linear and the angular momentum. In graphics, elastic forces are also often referred to as internal forces, which is in contrast to external forces. In contrast to internal forces, external forces do not necessarily preserve linear and angular momentum. For instance, if a force accelerates an entire element or object, then we have an external force. That's it about the first part of the discussion of elastic objects. Thanks for your attention.